Ah, there it is. So I'll get a little lower. One of the few times in my life I'm too tall for such scenario. So we'll come down here. Oh, wait, I got to pause. I'm sorry, but this is the first day of class. So I have to pause and. All right, so there's two kinds of charges, Z and M1. There's two kinds of charges, positive charge and negative charge. In this universe, negative charges, the fundamental electric charge that's negative is on electrons. For this kind of stuff that we see every day, the fundamental positive charge is on protons. The charges are to the experimental determination beyond belief of the human mind are exactly the same. And in fact, if they were even 1 part in a billion different, you would not be able to live because the forces wouldn't cancel. You wouldn't be able to aggregate this number of molecules and atoms in your body if there was a small imbalance of force. So the positive charge and the negative charges are exactly the same. There's other kinds of charges. You all know this if you've taken chemistry. There's ions. You can strip an electron off of something and have a positive ion, or you can add electrons and have a negative ion and such things. But for us in this class, we are really not even concerned if it's protons or electrons for quite some time. We're just going to call them positive and negative charges. However, we define them. Inside of protons, inside of neutrons, there's even a more fundamental unit of charge, fractional units of charges called quarks. They have charges plus and minus 2/3 and plus and minus 1/3. And if you put an up, they're called up and down, strange and charmed, top and bottom. If you throw two ups, that's 2 times positive 2/3, that's 4/3. And a down, that's minus 1/3, that's 4/3 minus 1/3, that's 1. And you get a positive 1. If you take 2 downs and an up, that's minus 1/3, minus 1/3, plus 2/3, that's minus 2/3 plus 2/3, and that's why a neutron is neutral. All right. I think we all know also, just as a preface to what's about to be covered in weeks from now, because we're doing vector analysis to get everything set up. But bear in mind, all the vector analysis we're about to do has motivation that we need to describe electromagnetic fields. Electromagnetic fields are vector quantities. Vector has magnitude and direction. All of you have passed General Physics 1, General Physics 2. All of you have had a course in mechanics probably, or some such thing, or modern, with one exception, and I'm not worried about her. So everything should be fine. So let's talk about vector analysis. So this is chapter 2. Can everybody see my screen? All right, who's going to be the ombudsman of my technique? I'm going to try to have a better writing technique. I'm also going to clean the language up entirely. Not one time this entire semester will a bad word come out of this mouth in this room. Not one time. If you're going to get donuts, you're going to have to earn the donuts by finding my typos. Not one time. Skepticism? Nobody's skeptical? Y'all think I can do it? You don't think I can do it, do you? All right, we'll see. We'll see, skeptics. Chapter 2, vector analysis. And I'll drop the link for the YouTube in on a canvas in a little bit. It's actually MRE_physvids, and I may change that. But I'll send it on Canvas anyway. It's the same one you had in General Physics 2. Same YouTube page. Okay. Electric magnetic fields are vector quantities, E and B. Those are the symbols for the electric and magnetic field later on. So these are vectors. And you have a pretty good background already in vectors, but you don't have everything you need from General Physics 1 and General Physics 2, because we are in the business of not just doing vector algebra, we will also be in the business of doing vector calculus. And vector calculus involves a little more machinery than we introduce you in PHY 2048 and PH 2049. But you know one thing, a vector is a quantity that has both magnitude and direction. Vector A. And if you tack on a coordinate system here with X horizontal and Y vertical, and I'm going to stay in 2 dimensions for my figures because I can't draw them in 3. And this is the angle theta. We know right away that AX will be A magnitude cosine theta, and AY is equal to A sine theta. Notice that A squared plus B squared is this AX squared plus AY squared. That gives me the magnitude because cosine squared theta plus sine squared theta. 1/2. We take the magnitude by taking the 1/2 power of the squared components. Another way to write that is ax squared plus ay squared, square rooted. And I interchange 1/2 and square roots depending on what my eye likes. Any vector, and this is trigonometry. That's all that is. Any vector can be expanded in terms of a set of unit vectors, and this is one of the very first non-trivial things we teach you in General Physics 1. We have a set of unit vectors, I hat in the x direction, plus j hat in the y direction, plus k hat in the z direction. So it's ijk. And generally in this class, I put I hat here. I'm not long for this world. J hat up in the y direction and k hat out. And why that k hat is out in that direction and not into the board, we'll specify later when we start talking about the right-hand rule and right-handed coordinate systems. Something to ponder when you look in the mirror. You see your right and your left flipped, but you don't see your up and your down flipped. You're not standing on your head. Something to think about why that doesn't happen. We'll get back to it eventually. Vector addition, subtraction. This is a very brief review. Is accomplished by adding the components or subtracting the components separately, and so on. And if you're not taking notes at this time, I don't blame you. You know all this already. And just as a quick reminder, in case we actually need it, brief reminder, not in the notes, but the way we add vectors, if we have a vector here, vector A, and we have a vector over here, vector B, the way we add vectors is by sliding the tail of either. It doesn't matter because vector addition is commutative. If it's commutative in the addition, analytically, it darn well. I almost went 12 minutes with breaking it. I only went like 12 minutes. It's darn well true that if it's additive, commutative, analytically, pencil and paper with equations, it should be commutative as well graphically, and it does. It doesn't matter if you slide the tail of B over here, be the ball, Danny. That's a reference from Caddyshack for those of you who are, none of you are old enough to remember it. So if you've ever seen it. So it goes here and then first tail to last tip. So this is A plus B. And if we did it the other way, leaving B where it was, here, not as good of an artist as I was hoping to be at a younger age, but there we go. If I moved A and slid it, we create a parallelogram by sliding A over here. And A plus B is the same in both cases. So that's a brief, very brief review of how to add vectorially on a piece of paper with arrows. All right. The first non-trivial thing you've still seen, we just did it all of addition and subtraction and graphical addition and graphical subtraction because obviously if B points this way, the negative of B is in the opposite direction. If A points this way, the opposite of A is in this direction. So that's great. The first non-trivial relationship is the scalar product. And it produces it really is a measure, if you read this, the scalar product is really how much of one vector lies along the other one. If we define, if they, not me, if they define back then the vector product is A dot B, scalar product rather, is A dot B, is AB cosine theta. That cosine theta factor immediately tells you this. If the two are lined up, if here's A and here's B, the cosine of the angle between those is 0. They're parallel. A and B are parallel. Parallel. So essentially, the shadow of B lies entirely along A. So that's a limiting case. And your physical paradigm for that example is work. If you're pushing something in the same direction, if you're pushing with a force in the same direction in which the force is being exerted, you get a maximal amount of work done. If you're pushing it opposite, you're slowing it down as best you can. If it's perpendicular, you do no work at all. Because when cosine, this is theta is equal to 0, because when cosine theta, if here's A and here's B, There is no shadow short of you could argue it's a point. Can't even see a point though. So here's A and here's B. B produces no shadow on A. And cosine of theta in that case is 90 degrees, and you get nothing. Because I assume no one knows anything, and because I always belabor every point and overtalk every point, if you've ever wondered, well, how do I do the angles when I have two vectors? Basically, all of vector calculus really has the angles measured tail to tail. So just slide them around and always put them tail to tail, and that will always define your angle. So it's just something worth knowing. Slide them around. On a flat piece of paper, just to whet your appetite for more complicated things, you can slide vectors around and they retain their orientation, their overall identity on a 2D plane or in 3D space. If you put vectors on spheres and move them around, they don't retain they don't retain their orientation. It very much depends on the path you take. But for us in two dimensions, you're doing this, 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 this. The vector will, so long as you keep it in a very sensible, you move it around sensibly as you would intuitively expect, it stays where it is. All right, good. We also know because of this definition, I hat dot I hat is 1 times the cosine of 0. Because anytime you have a vector in the same direction, the cosine between the vectors is 0. Got some in your eye? It's a terrible feeling, isn't it? Can you get it out? Because I spent a week with like an eyelash that fell into like a small pore, and I thought for sure, I was going to go blind. It was so miserable. You gonna be all right? All right, 'cause we'll get you. We'll take you to the ER right now. I want you to get that out. I don't want you going through what I went through with that little eyelash in the pore. Ah, feels like there's a stick in there, you know? All right, cosine of 0 is 1. We don't need to put that in a bracket. So this is 1. Same thing with j hat dot j hat. Same thing with k hat dot k hat. These are all equal to 1. It's 1 times 1 times the cosine of 0, which is 1. All the others are, of course, what? All the others are 0. Why? Because when we evaluate, for example, this is 1 times 1 times the cosine of 90 degrees, pi over 2, whichever one you prefer, and cosine of 90 degrees is 0. So if we had a chart of I hat dot I hat, I hat dot j hat, I hat dot k hat, the advantage of knowing all of you and knowing from what I saw, at least in my seminar class with you guys, you're all competent people. I know you're all competent from general physics. You're all competent people. I don't necessarily have to put every chart in every time. I know you can fill this out yourself. Yada, 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 yada. I don't have to carefully do that. What I expect you to be able to do, what I expect you without hesitation to be able to do is if I were to wake you up at 3:30 in the morning, looming over you. I wouldn't have broken into your house. I would have got permission from the landlord. Looming over you, I'd wake you up and go, what is J hat dot K hat?
0.
Excellent work by you. The first appearance of excellent work by someone. Okay. Did I do that in general physics? I did. I did that in quantum mechanics. Quite a bit. We were talking about that class. Another faculty member to myself, probably the best graduate collection of graduate students we've had in a very long time. It was really, you guys did something that I hope this class does, which is when the class is over, you guys talked physics. That's what I'm hoping to see. Not even necessarily about this class, but I hope you guys talk physics. All right, excellent work by all of you so far. So in class exercise, so I've set this class up. This set of notes was actually going to be an online course for a master's degree if someone wanted to do it. So I've kind of amended it. And the in-class exercises used to have like short videos, but the in-class exercise is you. So I want you to take this, and I'm going to give you a minute and 30 seconds. You have two vectors. A is equal to, and I'm going to shorten it a little bit. just for the sake of time, minus j hat. So it's not going to appear. You might want to revisit, or if you don't want to, that's fine too. Minus 3 I hat plus j hat. So in the bottom of the page, it's 2 I hat minus j hat plus 3k. And if you don't have the notes open, it's got all three ijk components. Let's not do that. So use the relationship to find the angle. It's got two pieces here. The first piece is AB cosine theta. The second piece is AX BX plus AY BY. And we don't need AZ BZ because these doesn't have components. So take a minute here, and I'm going to go ahead and pause. Literally 1 minute. I don't need you to evaluate it with the calculator. So let's do the first piece. The magnitude of A, we need the magnitude of A. Let's get it. The magnitude of A is 4 plus 1. That's 2 squared plus minus 1 squared. In my general physics class, I actually sat there and wrote out 2 squared plus minus 1 squared. I don't even think I need to do that with you guys. So this is the square root of 5. The magnitude of B, you should immediately have as the square root of 10. That's 9 plus 1. Everybody getting that? You feel good about that? So I now have, according to my first prescription, let's get rid of that. Am I recording? Yes. This will be the square root of 5 times the square root of 10. So currently what I have is the square root of 50 cosine theta. And what do we have for A dot B using the sum over index formula? Why I call it the sum over index formula, you'll learn later. That is 2 times minus 3, that's minus 6, plus minus 1 times plus 1, that's minus 1. And I see that cosine theta is equal to minus 7 over the square root of 50, or as it would appear on my general physics exam, theta is equal to the inverse cosine of negative 7 over 50. Everybody getting that or something like it? Any questions on that? We got to get this now. We have to address this now, and we're going to be together a really long time. So not being shy. Did I screw something up already? Square root of 50. That's not enough to get the bonus 50. That's not enough.
Tickets for 2 hours.
What?
I wish you had a dollar cut.
You know, I'm talking a mile a minute up here, and I'm like 3 times older than all of you. What do you expect?
So cheap.
Is there any other way to get what? I can't think. Well, you could graphically do it and get it with a protractor. I can't think of any other way. Yes, actually, let me read. In the context of what we've done so far, no. Is there another way to get theta? Yes, which leads us to the cross product. All right, leads us to a cross product. So that's the scalar product, and we will use this repeatedly, and it won't be this simple. And the reason it won't be this simple is if you took General Physics 2, and remember General Physics 2, there's a whole lot of stuff in there that involves Gauss's law and integrals of the electric field over lines and magnetic fields over areas and magnetic fields over lines. So it's not just A dot B. It's going to appear in the context of vector calculus, not just vector algebra. All right. The next, and really the last part of the review is the vector or cross product. We're doing good on time. You know what? Just because I want us to get off on a good start, I'm going to go ahead and take the 50 cents on that, even though I shouldn't have to. I'm going to go ahead and take the 50 cents on that as a gesture of goodwill. As a gesture of goodwill. I'm going to take the 50 cents. You're going to, who's keeping track? You're going to keep track? So vector calculus. I can't, it would have been so much cooler though if you had worked at a fried pickle joint instead of a pickleball place.
16 an hour to do nothing.
Yeah, and then you would have come home smelling like fried pickles, and who wants that? Right. So vector calculus, the cross product. I'm not going to say continued. Just go to vector cross product or vector product. Nothing there. So vector product, you also learn this as the cross product. It's called a vector product, or in quotes, cross product, because it involves a cross sign. X sign. So that is defined this way as A cross B will be equal to, in our case, magnitude of A times the magnitude of B times sine theta times a unit vector that points as determined by the right-hand rule, and it is a unit vector. Normally, we don't even worry about that unit vector. Normally, what you'll see most of the time is this written, because the magnitude of a unit vector is 1. You'll see this most of the time written this way. You can normalize to get that. That just takes a piece of the algebra out, where you have to normalize whatever A cross. Just as a technical point, A cross B can have three, in general, A cross B in three-dimensional space can have I hat, J hat components, K hat at the end of the calculation. And it's not worth generally, unless you really want to know the direction as a unit vector. Most of the time, you'll just get it with a right-hand rule. The right-hand rule is this. Here's A. First of all, here's A and here's B. And just to emphasize that this is not how you want to do it, you take that vector B or that vector A, I don't care which one you do. You take that vector B and you slide it down so you can put it tail to tail. So you take that vector B and get rid of it and draw it somewhere else, which is namely here. So let's do A cross B. And I purposely did this a little more complicated than I would do it for general physics. In general physics, I would have put the A on the bottom and the B up top because that would be more transparent. But why should I do you any favors? You just charged me 50 cents for a trivial error. So let's do this. I'm bitter. 30 minutes into the class and I'm already bitter. All right. So A is this one, B is this one. The goal is to push A into B with your right hand. If you are left-handed, I'm sorry, the world's not set up for you. Physics is not set up for you. What you do is you're going to push the first vector, and I'm going to move that A. It offends me. Put it here. So I'm going to take A, which is this pencil. Now, there's a lot of ways to put it in the palm of my hand. Since I'm going to be pushing it, I need it in the palm. First of all, none of us are circus. I can't use the word circus people. Okay. We're not a circus act. We can't push like this. We have to push like this. Our goal is to make like the royal wave. Hello, peasants. So we're going to take the palm of our hand and put it here. Now, there's a lot of orientations that I could put that vector A in the palm of my hand. Could do it here, could do it here, could do it here. But the goal is, it's like playing chess. You need to think one move or two moves ahead. You're going to push it here. You're not going to push it that way. You're going to do the most natural, relaxed motion possible. You're going to push it into that. This doesn't do you any good. This doesn't do you any good. You're going to push it nice and relaxed. Think about clapping your hands. Okay. So whatever the second vector is, maybe you put it in the palm of your hand here with your left hand and you push. You see your thumb? You have to say you have to have a thumb of purpose. You can't have a thumb that lacks vim and vigor. Your thumb has to have purpose. You see the thumb? You see this? That's not a thumb of purpose. You see this? That's not a thumb of purpose. See that? That's a thumb of purpose. Look at the strength that thumb gives you. Look at the power that thumb gives you. You see that thumb? That thumb would get a hitchhiking person anywhere they wanted across America if they stuck it out there on the side of a road. That's a long drive. Okay, it would get you. It would get you to the Junior Food Mart on Perry in Perry, maybe. Okay, assuming you didn't meet a violent end from a psychotic hitchhiker, which if you watch enough horror movies, you all know that's how they end. Like the Hitcher. Anybody, if you ever see the Hitcher with Rutger Hauer, who was Roy Batty in what's the name of the movie? I can see it in my head. Blade Runner. Blade Runner. All right, so A cross B in this case is into the board. And we indicate A cross B. Another reason I drew it this way. A cross B and into the board is with an X. This is with an X like that. That's into the board. Out of the board, if we did B cross A, and I think it's readily apparent to everyone in here that A cross B is minus B cross A. B cross A, here's B. So B is the first vector. I put it in the palm of my hand and I push it into A. And notice my thumb is pointing right at my forehead. It's out. B cross A, it's out. So here we have B cross A indicated that way. That's the arrow tip and the arrow tail. So the tip's coming out at you out of the plane of the board or iPad, and the X is going in. So that's the convention in this class, and I don't think there's any exceptions. To go back to Mr. Euler's question, is another way to get the angle. Let's go back and actually use the same set of vectors. I have them. In fact, I think I just copied and pasted the same set of vectors. So we'll do it again. So A cross B. So A is equal to, I'm going to write them again. This is an in-class example. The difference between, or in-class exercise, there's in-class examples and in-class exercises. And the in-class examples are a little more elaborate. And I kind of walk more than the in-class exercises tend to work along with you. So, what is it? 2I hat minus J hat. And then B is equal to minus 3I hat plus J hat. So before we start, we have another table to construct. And we already know from the definition of AB sine theta, the sine of 0 is 0. I'm going to need a little more room. This time I am going to construct this table. I hat cross I hat is 0 because I want to use the right-hand rule, which I didn't have to do with the scalar product. How are we doing on time? We're doing good on time. I hat cross J hat, X this way, Y up, I hat cross J hat. If you didn't see that, I'll do it again. Have a look at the board or have a look at me, either one's. I hat cross J hat, X coordinate, Y coordinate, I hat cross J hat, bam. Thumb of purpose is right at my forehead. That's out. That's K hat. I hat cross K hat. I hat's this way. K hat's out of the board. Now it takes a little bit of effort. I can't do it that way. You can do it like this. Look, you do it like this. So there's I hat, K hat's out of the board. Push. See that? That's this way. Okay. So I hat cross. Oops, I need a thumb of purpose. I'm having trouble. Push in, that's down. That's minus J hat. You're almost done. J hat cross I hat, I don't have to recalculate. I know that's minus K hat. J hat cross J hat, I don't have to calculate. I know immediately that's 0 because the sign of those two vectors, the relative sign is 0. J hat cross K hat. J hat is up, K hat is out. J hat is up, K hat is out. J hat is up. Here's J hat. K hat's up. Thumb of purpose points to the right. That's I hat. And these are all done already. Because K hat cross I hat is minus of that, which is J hat. K hat cross J hat is minus I hat. And I hat cross, or K hat cross K hat is 0. Of course, we don't do it that way. How do we do it? Well, I don't do it anyway. I do it in my head and out there. I've been doing this 45 years. The best way to do it, if you want a little mnemonic memory device, is here. IJ gives me K, JK gives me I, KI gives me J. If I go opposite, swimming upstream like a salmon, you pick up a minus sign. And that's the easiest way to do it. So A cross B will be 2I hat. I'm going to write this one out a little more elaborately here. Cross minus 3I hat plus J hat. I hat cross I hat is 0, so I get nothing from the 2 times minus 3. And I get 2 times 1, which is 2. That's K hat. And then plus, here I have minus 1 times minus 3 times minus 1 K hat again. So that'll be plus minus K hat, and this comes out nice. I believe, unless I made an arithmetic error, this is just K hat. So this is 1 K hat, if we're going to be explicit about that. And AB sine theta, we compare to 1. This we already saw earlier was the square root of 5. This we saw earlier was the square root of 10 sine theta. So this gives me theta is the inverse sine of 1 over 50. And if you calculate square root, square root, square root, square root of 50, and if you take your calculator out and calculate -7 over the square root of 50, and you can check real quick that that makes sense, right? How do I know that? Because if you look at what cosine was and square it, you get -7 over the square root of 50. That's 49 over 50. If I take sine theta, which was positive 1 over square root of 50, and I square that, that's 1 over 50. 49 plus 1 is 50. 50 over 50 is 1. Cosine squared plus sine squared is equal to 1. What's the matter, Summer? You don't believe me? Go back over here and look.
-3, and it's negative, gonna be,
There's three negatives, right?
right, so it'd be -3, not -1 on it. Okay, yeah, I was confused about that. Yeah, so it'd be -k.
Okay. That's -k right there.
No, the final answer ought to be -k, because that k would be -3, wouldn't it?
Okay, let me do it. Did I write the problem down right? So I cross J is K. That's good, right? Then I have negative, negative, negative. That's three negatives.
Yeah.
Oh, is it a 3 is what you're telling me?
Yes.
That's 3. Is that correct? -3. 3, 3, it's still, it's -1. This is like double jeopardy. I should only be fined one time for the same type of mistake.
Like $1. Well, that was square root.
I'm going to take this one under advisement. We'll see. All right, I'm going to wait. Okay. Again, these are plus and minus things. Although my justification is as a theorist, I don't really care. I can tell when the answer is wrong when I'm done. You know. Notice, by the way, it still get cosine squared plus sine squared theta equal to 1 because the minus sign will square out. So you're good. So that was a second in class exercise. So we just did vector algebra. We just did vector addition and subtraction. We just did vector multiplication. Yes. Thank you. Yeah, I'm recording. I am. So let's go ahead and do now vector calculus. And immediately the ante is upped. We start with probably, I think, the most ubiquitous symbol, the most often used mathematical object in this class, which is known as the gradient. Also known as del, also known as nabla, but whatever you want to call it, it's defined this way. Grad. I'll try to be consistent about putting a little vector over it. This is I hat partial partial x. You say, why would anyone need this thing? It's deep, man. That is a vector operator. This has the goal. Its goal in life is to find a scalar function on which to operate. Quick example. So quick example. Well, let's do it this way. The first thing you can do with it is what's called taking the gradient. And this is trivial, very trivial. You just calculate the derivatives, partial derivatives of x, y, z. It's all fun and games until you're in spherical coordinates, by the way. We all know how to calculate a derivative, presumably. Here's and this is a really, really important idea. Okay, and I'm going to come back to it once we get, we're going to do a practical problem, and then we'll come back and I'll give you the theoretical argument why this is true. The vector that results, and I'm going to write this down to emphasize it in caps, the vector that results from, and I'm going to use S here, not, no, I'll use F. Results from grad F is normal to the surface defined by, you see when I'm writing out in big capital letters like this and I'm writing out word for word, that means it's really important. X, Y, Z is equal to C. And I'm going to remind you of something here, because not everybody throws around differential geometry for a living the way I do. This is what defines a surface. This is an aside. You'll see here I write discussion. If you look at the notes, it says discussion, f of x, this is a surface. So what does this mean? Let's look at this. X squared plus y squared plus z squared. Let's say this is less than c, and we'll just, for convenience, make it 1, less than or equal. What is this? This is sphere. It's a solid sphere, isn't it? Because all the points less than 1 are included. And by the way, that is a closed set. When you include the boundary, that's called closed. This is a sphere. And by the way, that is a full three-dimensional object, is it not? It's a full three-dimensional object. It's a sphere with stuff in it. All the points, like an orange, like an orange. So we have x squared plus y squared less than 1. If I set this less than or equal, if I set it just less than 1, I now have a sphere, but it's an open sphere. The boundary's not included. By the way, for those of you who are double majors, I think one or two is a double major. That's where topology really, open sets is what topology is really all about. However, I can change that solid sphere into a surface by setting it equal. That's what that equal sign does. Because now I can no longer pick x, y, and z arbitrarily subject to condition they're less than 1. Now, if I pick x and y, z is fixed, correct? So in fact, if I wanted to, I could turn this around and write this. And you have to be a little careful, plus and minus, and that would plot the surface of a sphere. The plus would give you an upper hemisphere, and the ones below would give you the lower hemisphere. Setting a three-dimensional function equal to a constant, that's what this is discussion. That's what you need to wrap your mind around right now. Setting a function of x, y, z equal to a constant immediately produces a surface. You also maybe have seen that. I don't know if they do this anymore. You can have something like an ellipsoid. Doesn't have to be a sphere. You could have something like that that's an ellipsoid. You can have anything you want. But it's f of x, y, z equal to a constant, takes a volume and turns it into a surface because you're constraining. Essentially, what are you really doing? You're eliminating one dimension, aren't you? You're eliminating 1 degree of coordinate freedom because once you pick 2, the third one is fixed by the condition that it's equal to, not less than. All right. So let's do an example, in-class example. So I'm going to, how much time I have? We're doing it on time. Here's S. I'm using S now. And the reason I am is because I'm only doing it in 2 dimensions. So this is x squared plus y squared. And I'm going to set this equal to 1. Now, you normally don't think of a surface as a circle, but it is a circle. It is a surface. It's just a surface in a lower dimension, isn't it? This is I'm really reluctant to do this, but I'm going to do it anyway. That's the interior of the sphere that we drew before in 2 dimensions, as opposed to 3. This would be a disk, right? That would be a disk. Less than 1 would be a disk. The split second I set it equal to 1, it now becomes a surface, but it's not the surface in 3 dimensions. You just got to let your imagination. In fact, it's easier. It's a surface in 2 dimensions. So it just takes a 2-dimensional area and encloses it. So here's our circle. That's a bad circle. Let's just get rid of all of it. So here's our circle. See, this thing will let me draw a circle and then not punish me. So I got a little bit of theory background for you. Let's see how it plays out in a real life example. And then I give you the theoretical justification when we come back on Wednesday, or you can look it up. So the first thing we're going to do is draw a graph for s of xy equal to 1. I just did it. This is part A. Part B, we're going to calculate grad s of x and y at a bunch of points. We're going to calculate grad S of X, maybe do a chart might be better. And of course, when LaTeX, I didn't feel like drawing pictures and all that. If you guys know anything about LaTeX, you want to do that. So here's X, here's Y. I've got them listed, but this is what they are. First of all, notice I have to pick these points in accordance with my constraint that x squared plus y squared is equal to 1. So when we come back next time, it's 111. So when we come back next time, we're actually going to finish this problem. I would encourage you, if you have the first week of class, you got nothing better to do, you're riding the bus to the Mag Lab or anything like that, or to CPAS, go ahead and finish the problem. Go ahead and finish it. Take grad S, which is easy enough to do. Notice I'm just introduced a new notation. That partial, I just wrote partial with a subscript. That means derivative with respect to x, derivative with respect to y, respectively, of x squared plus y squared. And when we come back next time, we'll continue right from there. All right? Excellent work by everyone today. And we will stop.